Okay, so welcome to today's session. This was recorded some time ago, and it was with audio, so we have to go through it again. It's just an opportunity for us to go through the concepts once again. Okay, we are looking at the chapter 3 of the drive. So yeah, you already know who it is. It's of course code already. At the beginning, we're going to revise all the revision of finishing motors. We are going to see how we can control speed and torque of finishing motors. Start by revising some concepts we already know from synchronous course in second year. So we look at the construction of induction motor. We look at their principle of operation. Then we look at the equivalent circuit. We do the analysis on that. Okay. So let's see if you have any question. You can raise your hand, or yeah, you can raise your hand, or you can put it in the chat. As we go on, I'll be taking your questions. Please ask for any question. The goal is for you to understand. The goal is not for us to finish. So put that in mind. Okay. Okay. So this is just introduction. So in course, there is this assumption that you're already familiar with the basic design and operation of screw gauge induction motors. Even though I'll take some time to explain what I think should be explained forward. Yeah, so we assume that you already know the basic design and operation of screw cage induction motors, which are just types of induction motors. We have the squirrel cage induction motor, and we have the one rotor induction motor. I'll speak about that very soon. Okay, so we already know that. So we already know how they work when they apply from a fixed frequency source with a fixed amplitude. So I mean, when we're doing that, most of the questions that we were looking at when they are operated from a 50 hertz supply, maybe let's assume line to line uh, voltage was 4.5. Okay, in this case, what we are looking at differently from the one we already know is in this time around we want to change the amplitude of the supply and would like to change frequency of the supply. Okay, so we are going to add a variable frequency, variable voltage drives. Okay, so now let's go on and look at yeah. So that's mentioned. So electronic drives cause focus on the operation of variable speed in that motor drives that affect from a variable frequency and variable amplitude. Okay, we'll see how we can able because the pump that comes into your house or comes in your industry has a constant frequency. Okay, that's 50 hertz plus or minus what 5 pence, right? And if you are if you are if you are in if it's in a single phase load, the line that comes into your house supplies your 240. Therefore, there is nothing you can do. So if you are getting a three phase, you are getting the three phase into your let's say industry, the line your voltage is so 415, right? So 415 volts. So then if you want to increase this, if you increase this volts, you have what apply special what equipment like contest. So you can do it. Whatever you get can what rectify it because there is no you can take an AC without rectification. Just take the AC and just change the amplitude and the frequency. You have to first of all what rectify it. Then you construct a new what AC from it. Okay. Then during the construction you are able to change the frequency or change the amplitude. So we'll look at how to do that very soon. Okay, so let's go on. Okay, so these are just the objectives of this chapter. At the end of this chapter, you should be able to grasp this or be able to know all the things here. Okay, So let's look at the nomenclature or this is how they call it. Another name they have for it, I remember. Yeah, so okay. Yeah. So these are something or some variables, let's call variables or some convention we are going to see in the slide, and we want to know what they stand for. Okay, so this slide, if you see small p, small p like this, is for what? Purpose. You know from synchronous cause that 2 times small p is equal to what? The capital, which is the what? Total number of poles. Okay, so if you have a machine, a two-pole machine, it will what? North pole and a south pole. Okay, then in here, the total number is a pole on it. This is a pole on its own, but the pole pair, a south pole and north pole from what? A pole pair. So then, okay, so this is a pole on its own. This is a pole on its own. Okay. Remember, asynchronous, the total number of poles in a machine is always an even number because nobody have 7 poles and have what? 6 south poles. Okay, every not password and corresponds to the total number of poles in a machine is not an even number, but the number of poles can be an even number, can be an odd number. Okay, so if these you are going to see in the course stand for what? Then we have to call we have FE. FE is what? The frequency of the supply voltage. That's FE. Okay, sure. So yeah, then we know omega. Omega is equal to pi F. Okay. So then if F I'm using in the supply is the line frequency, then omega I'm going to get to be omega equal to pi F E. That's going to be what? The angular frequency of the theta. Is that okay? It's the same as what the synchronous speed was right president. I'm going to very soon we will know what synchronous speed is. So this omega here is here in right second, and it is frequency of what the rotating magnetic glass in the M. Okay. So you can see it was Fs. So if you see Fs, it's the same as what if you see omega S, it's the same as omega E. Now let's go to synchronous speed. Okay, so then let me use the opportunity to say how the individuals speak in order to understand synchronous speed. Okay, so we're given synchronous speed from second year, and after some of us don't know what synchronous speed is. So given that you have first data, your machine has data and it has root two. Okay. And in between the data and the root two, or the data port and the root two, what that have. This magnet is something undesirable. Without it, the photo cannot work. In the sense that the root is the okay. In the sense that the root, which is the rotating part of this machine, needs some it needs some medium over here to root in it. Okay, so assume we decided to make the space, decided to leave space between the stator and the rotor. The question is, how is the rotor going to rotate in order to cause the shaft to what rotate? Because the shaft is what kind of clamped to rotor. It is the rotor movement that causes the shaft to move. So if you've seen a blow before and see the shaft moving because the rotor is moving. Once the shaft stops moving, once the rotor stops moving, the shaft needs to stop. Is that okay? So then this roto over is going to need some medium in here, okay, so that there is some kind of space between the roto and the stator. Okay, a little bit history. So when like our forefathers, God bless them, amen. Okay, let's go on. So when they started designing these tools or even the generators, okay, let me say this later. Okay, so let's go over synchronous speed for now. Yeah, so synchronous speed, as I said, it is the speed or it is the speed at which the flag in this egg, egg medium okay rotates. What happens is that for a three-phase, in this course, we're going to look at what three-phase induction motors. So all the motors we are going to look at here are what three-phase motors. The single-phase motors, look at them in what the special machines course. Yeah. So three-phase motors are self-starting. That means they are able to start on their own without anyone's help. Just supply them with what three-phase voltage. They will start on their own. But single-phase motors are not able to start on their own. And we're going to talk about why that. But in three-phase motor, when you supply three-phase voltage to it, so you have phase A voltage, B voltage, and you have phase C voltage. Three-phase current is going to flow towards the windings. Okay, look at the construction of the motor very soon. So when the three-phase current flows, it's going to produce three-phase what flux. So you are going to have phase A flux, there is B flux, and what phase C flux. Okay, and because flux are displaced from each other by an angle of 120 degrees, three-phase, because the voltages are displaced by an angle of 120, the currents are displaced by an angle of 120. So the flux are all what displaced by angle of what 120. Because of the angular displacement between the flux, there will be what interaction between the flux. Even though there's an angular displacement between them, theoretically they are peaks or they are peak flux, okay, or amplitudes what. Then so the difference is just phase shift. They are going to interact together. These three flags are going to interact based on what angle between them. When they interact, that they are going to produce resultant flags, and this resultant flags, which are of phi amp, is good. Well, it's a rotating flag. It is not a oscillating flag. It is a rotating flag. Very soon we'll look how the rotation happens. This rotating flag is going to what? Because it is rotating, it's rotating, right? So it should be rotating at a set speed. The speed at which it rotates is what we refer to as what the synchronous speed. And this synchronous speed is a function of what the supply frequency and also a function of what number of poles. So from asynchronous, we know synchronous speed ns or nz is given as what either you write this 120 f divided what capital P, right? Or you write as what ns equals 60f divided by what small p. Is that okay? Because 2 times the small p equals to the capital P. So if you substitute this over here, you have to get what 60 on what this on this. Okay. So it means that with the same supply frequency, if the motors has the number of poles, they are going to have different synchronous or speeds. I hope it makes sense. And if you take two machines that have the same speed with different supply frequencies, they are going to have what different synchronous or speeds. I hope that makes sense. Okay. So if you have now, we now know we have a certain speed, synchronous speed, which is the start with what the rotating flux rotates in the air gap. Now, when this flux rotates, it's going to cut what it's going to cut the armature conductors, and when it cuts armature conductors, it's going to induce an EMF in them. When that happens, okay, we'll look at something down there. When that happens, current is going to flow the armature circuit. Once current flow, Then you are going to remember the rotor and armature circuits found in what? A magnetic what? A magnetic field. So then if current starts flowing through the armature circuit, you are now going to have conductors placed in a magnetic field. And we know from, I think, was it I think Lenz's law or somebody's law, we only care about what the person says. Yes. So when you have a conductor placed in a magnetic field, if you have a current carrying conductor, not in a conductor, if you have a current carrying conductor placed in a magnetic field, from I think Lenz's law or what law it is, there is a force that is going to what exerted this conductor. When that was so one side of the force, so the force is actually what? A couple. So when we say a couple is just two equal forces with what acting in opposite direction. So if I have this, so maybe this is a force F, this is a force F. Okay, these two forces form what a couple. This is acting downwards, this acting upwards. At the end of the day, they are going to rotate this in the same direction. Okay, then you are going to have two forces. You have to have a force acting on this. One of the force, you can determine the direction of the force using is it Flint's left hand rule and then his right hand rule. Okay, if a generator, you use the right hand. If it's what, to use the left hand. Because I'm camera, so I can't do it. Yes. So you can try it on your nice. Okay, let's go. So this the force is going to act on this conductor. So because forces acting here, one is acting downwards, one is acting upwards, based on what the direction of the current. If one is acting down, one is acting upwards, it's going to cause these conductors to move. Okay, so this to cause the rotor to move. Then the rotor will from what? A speed of 0 to a certain speed. Let's call it n. Okay, so the speed at which the rotor is moving, it is what referred to as what the speed of the motor. Okay, it is that speed that you measure what at the output of what the motor, or it is the speed at which the shaft rotates. So that speed is what the rotor speed or the rotor speed, and it can be measured in revolution per minute or radians per second. Okay, so when this happens, the rotor is also going to rotate at what a certain frequency. And if you multiply that frequency by pi, that should give you what? Angular speed of what? Of the rotor. Okay. Now let's to electrical speed and mechanical or electrical. Either you call it electric, let's at electrical angle and mechanical angle. This thing has been confusing a lot of people. Let's address it. Okay. So if you take a motor or if you take a circle, the total angle we know from mathematics, physics, wherever, total angle you can have in a circle or the total internal angle, okay, you can have is what? 360 degrees. And this is the maximum mechanical angle you can have. But we electrical engineers, we said that out of 360, we can get even 1080 degrees. Okay. How does this happen? So if I have a motor, depending on the number of what poles I have in motor, I can have more than 360 degrees in the motor. Okay, so from asynchronous, you know that these motors, the poles are placed what? One pole away. Okay, let me use this one to explain this. Okay, so if I have a motor, oh, sorry. So if I have a motor like this, and I have this pole, have another pole here. Let's call this the south pole, and this is the north pole. From asynchronous, we know that these poles are placed what? One pole pitch away from what? Each other. And we know that in electrical engineering, if we say pole pitch, that is what 180 degrees. So one pole pitch. Okay, this is triggering some people's yow, but it's fine. So one pole pitch. Okay. is what? 180 degrees. So then if I have two poles, this is what? 180 degrees and this 180 degrees. Then the total electrical degrees we are going to have is what? One pole pitch as one pole pitch. That would be what? Two pole pitches. And two pole pitches, if pole pitch is 180 degrees, two pole pitches will be what? 360 degrees. Then in this case, we are going to have 360 degree electrical is equal to what? 360 degrees what? Mechanical. Is that okay? Then if I have another model that has what? Four poles. So this is south pole, this is what? North pole, and we are going to have so south, north. Okay, let's say we have the okay, so it should be south. This is north, right? This should be south, and this should be what? North. Eh, one case. Even though now the number of poles you have is four, but from this pole to this pole is still what? One pole each. Is okay. This is still one pole page. This is still one pole. This is still one pole page. At the end of the day, we are going to what? Four pole pages. And four pole pages is going to be equal to what? The total electrical degrees we are going to have is what? 4 times 180, which is equal to 720 electric degrees. But the total mechanical degrees here is still what? 160 degrees. Is that okay? So then we have two poles giving us what? So two poles giving us 360 degrees electrical. We have four poles giving us for 720. We are going to do six poles giving us what? Is it 1080? Yeah, I think so. 1080. If you have eight poles will give you what? 3000, what? I think 1140. Or yeah, you can calculate. Okay, then we can see that the relation in all days, the total in all of the total mechanical degrees was 360. Then we see that there's a relation between what? The number of poles and what? The total electrical degrees. Is that okay? So I have two poles giving me 360, four poles giving me 720. Then we have this relation that what? The total number of the total electrical is equal to what? The total number of poles on what? Two. So this is a big P or capital P or uppercase letter P times what? 360 the total mechanical degrees. So now let's look at, so if I have two poles, I'm going to have 2 divided by 2 times 360, which will give what? 360. If I have the total number of poles to be 4, I have 4 divided by 2 will give me what? 2. 2 times 360 will give me what? 70. 6 poles, that is going to go what? This place will evaluate to 3. 3 times this, that will give me what? 1080. I hope that makes sense. So this is the relation, or you can write it as the total electrical degrees is equal to what? Total number of poles divided by 2, or the pole pair, which is small. So this is what? Small p times what? 360 degrees. I hope this makes sense. Okay, now look at something else. Okay, so we know that angular speed is what? The change in what? Angular displacement with respect to what? Time. Okay, so if I want mechanical speed omega m will be equal to what? Change in what? The mechanical displacement with respect to what? Time. But I know, what if I want to determine electrical speed? I know electrical speed, let me call it omega e, should be equal to what? Change in electrical displacement divided by what? Change in time. We don't have mechanical time, we don't have electrical time. Time is time. Okay. So this is the change. But I know, so if I will find this electrical speed in terms of mechanical speed, I know what to do. I know what? Electrical displacement equal to what? Pole pair times what? Mechanical displacement. So then if I have the mechanical displacement and I still want to find the electrical displacement, I just multiply it by what open. The same way if I have mechanical speed and I want to determine electrical speed, I don't have to create. I know what to do. It's okay. So then, if I want to determine electrical, I'm going to get omega E to equal to what? P is a constant. So if you different, because constant, you just add that out. Then you have what? Change in what? Omega M. Because no omega E is equal to what? P times what? Omega M. So then I'm going to have this with respect to what? Time. Then in this case, whatever we have here is what? Mechanical speed. Then I can say electrical speed is equal to what? O per time what? Mechanical speed. Then if I have electrical speed too and I want to determine the mechanical equivalent speed, I just divide the electrical speed by the number of O per. I hope this makes sense. So I'm explaining all this so that when we get to the raw business, we don't waste a lot of time. Okay. Yeah, so that's what you have over here. Okay, then there is something with the sleep. Yes. Okay, yeah. Okay, can I read what? Like everything I've talked about so far or what? Please, you know, mute yourself and I don't get your question.
Please, can you go over the top one? What am I saying? Can you go over the omega R, the displacement over the time, that part?
Okay. So we already established these facts that electrical displacement equal to pole times what mechanical displacement. And angular speed in general is given as a change in angular displacement with rate to time. So this is a formula we know from physics, right? Okay. So if I want to find mechanical speed, if I want to find mechanical speed, find a change in what mechanical displacement with respect to time. If I want to find electrical speed, because electrical displacement is not the same as mechanical displacement. So if I want to find electrical speed, I just find a change in what electrical displacement with respect with what time. But I know, so we've already established this and this. What if I have one list and I want to find in terms of the other one? So assuming I have most of the time in things, or what you measure outside is what the mechanical speed. Okay, what you measure is mechanical speed, and you want to determine what the electrical speed. Then if the mechanical speed, I want to determine the electrical speed. What do I do? I know the relation between what mechanical angle and what electrical angle. I know that the mechanical electrical angle is what the pole pair times what the mechanical angle. So then I come and substitute into what? So I'm going to get omega E equal to what? Change in respect to time of what? P omega what? Omega M. Okay. Then if I want to differentiate it, this is a constant. So I just bring it out. Omega E should be equal to what? This differentiation, I P out. Okay, because the change that depend on what? Pole pair. The pole is fixed at the time they are what? Converting the motor. So then I have this substance, so I start this out. What am I left with? I'm left with a change in what? The mechanical displacement with respect to what time. But change in mechanical displacement with respect to time equal to what? Mechanical speed. Right? So then this should equal to what? O per time what? Mechanical speed. I hope it makes sense. Okay.
Yeah.
So we have to call sleep. So if you have a motor and motor, so the sleep is a measure of difference between what the synchronous speed or the rotor speed. Now we know what synchronous speed is. We know what the rotor speed is, right? So the rotor speed is just the speed of the rotor or the shaft, and the synchronous speed, the speed of what the rotating flags in the air. So then, if it happens that there is difference between the rotor and the flags, it introduces what we call a slip. So the slip is what the change in what the synchronous speed and what the rotor speed divided by what the synchronous speed. I hope this makes sense. So this is just a slip. Okay. So if this is the case, you can say that the synchronous speed minus the rotor speed should be equal to the slip s times the synchronous speed. This makes sense. And the relation over here, which is omega minus omega equal to s omega s. This is equal to what? Let me not put here. This here is equal to what? The slip angular frequency. Omega slip. Is that okay? So then this is the same as what? 2 pi fe minus what pi of fr. Let me say it that way. Then I can start this out. So this is 2 pi what? 2 pi out. They have what? Fe minus what? Fr. Okay, then I call this what? F was sleep. So then omega sleep is equal to what? 2 pi f what? Sleep. I hope this makes sense. So sometimes I go over the sleep again. So when we are starting the motor, the flags will start rotating, right? The flags will be rotating. Then it will induce EMF, the rotor, the current flow, then there's a torque generated. So if the torque that is generated is enough to run the inertia of the rotor will start moving. When the rotor starts moving, to start from was zero, then it will start accelerating. Okay, so that means the time starting the leap is equal to the sleep is equal to 1 because the sleep is equal to the synchronous speed minus what? The rotor speed divided by the synchronous speed. So at starting, the speed of the rotor is 0. So we will get omega divided by omega s that will evaluate to 1. So whenever you hear a question that is at starting, don't say that you weren't given what the sleep. It just is that you are not paying attention to the question because the sleep is in the question. In that case, the sleep is equal to what? Then, okay, so sleep is equal to 1 at start or at standstill. When you say standstill, it means the rotor is normal. And when you are starting a motor, the rotor doesn't start rotating before you start the motor. Okay, unless it's a prime mover that is driving what? The rotor. Like there's an external force driving the motor. Maybe like a turbine pulled to what? A turbine shaft coupled with the rotor. Something like that's how generators operate. You are looking at motor. Yes. So then as the rotor accelerates, you see that the omega R value over here will start increasing. And if that starts increasing, this value will start what reading from 1 towards what 0. Okay. So as the motor is accelerating, the speed will start to reducing. And if the rotor is able to accelerate to a speed equal to the synchronous speed, then your sleep counts for 0. So then in synchronous machines, their sleep is equal to 0. In synchronous machines, the sleep is equal to 0 because the rotor rotates at the speed of what? At the same speed as what the support, the rotating flags. So in a synchronous motor, yeah, the sleep is equal to 0. That's at not when it is starting. Okay. I'll talk about that. So for synchronous motors, they start as induction motors, but they run for synchronous motors. Don't forget this. They start as induction motors and they run as what? Synchronous motors. So that means when they are start have a sleep, maybe if the time I get to the operating principle, if I'm so happy, we'll talk about that. Okay, so I think the rest of my this I've already talked about it. IS is the current flowing through the stator. This is the voltage applied to the stator. Okay, this VM is for the voltage across the magnetizing branch. So, okay, I will talk more about this when we get to the equivalent circuit. See, I'm talking too much. Talking too much. 27 minutes. Okay, so yeah, IM is the current flowing through the magnetizing branch. RS is the resistance of the stator. Hey, understand English? Okay, let's go. Yeah, PI is equal to P. That's the input power. Okay, because for a motor is an electromechanical what device. You give it electrical power, it gives you a mechanical power. Okay, a generator takes mechanical power and gives you what electrical power. Okay, the rest of them I will say that. So T is the electromagnetic torque generated by what the motor. If the motor is not able to generate electromagnetic torque, that means it can't run the load. It can't even start in the place. Like it can't run. Yeah, basically that's what it is. And in order to overcome a certain load torque, the motor has to generate what? Electromagnetic torque. This electromagnetic torque, fortunately or unfortunately, it's a function of what the slip S, what we looked at here. So if your slip is zero in an induction motor, if the slip is equal to zero, the torque you are going to generate will be what? Zero. Maybe I will explain that later. Okay, so now let's go on. Construction of induction motors. Construction of induction motors. Okay. So I said earlier that induction motor has basically two parts. We have the moving part and what the stationary part. The moving part is what or the rotor or the rotor or whatever you guys call it. Yeah. Then the stationary part is what is called the stator. Okay. So we've all seen we've all seen motors before, right? So the car, this one you see, like what you see, the outside, the yoke and all that, the part of what the stator, and the stator also has what windings. Okay, so the stator you see, it's not like a full metal, like one metal, like molded. Okay, it's actually what small, small that they are sliced, then they are together. The reason why they are sliced and stuck together and not like one plate metal is because we want to reduce core losses. We know that I think so. When we talk about the core losses, we are talking about hysteresis loss and we are talking about current loss. Okay, I don't remember, but one of them was this on the thickness of the material. So then you want to reduce the thickness of material in order to reduce the core losses. The core losses you can't prevent them, like you can't prevent them. So what you do is what you reduce them. And so once like if you slice them and you don't laminate them, you put them together, they still have what like the contact is still there. So if you slice them and you don't laminate them, just like having the full metal like that. So you have to laminate them so that in a way they are kind of separate. They are stuck together to give you that full strength. Okay. Then I said earlier the stator has what winds. For the induction motors, the stator carries what field current. Hey, I said field. The stator carries what the field winds. But for synchronous machines, the stator is what the armature. Okay. So when we say armature and the field is just that winding that produces what the working magnetic was field. Okay, so that is the or the working magnetic or flux. So that is the field. When we say the armature, when we say the armature is just windings or the conduct in which what EMF is what induced. So that is the armature. So for the induction motor, the stator is what the field, and this field are what segment into what three phases, which are what specially placed by an angle of what 120. So that's why you have the yeah, that's why if you take the three phase generators, they generate what three phase, and like the angle 120 you see because of what the way they are what arranged. Okay. So from asynchronous, we know I'll talk about that when I'm talking about the amateur. So the star windings are carried in what slot? Yeah, this is why I'll say my story. So the theta windings are carried in slot around the circumference of what the cylindrical ball. You see the cylindrical ball over here. So yeah, this is cylindrical in nature. So what you have here, these are what the slots, and you can see that what these windings are placed for the slots. So yeah, so let me talk about myself. So when for so the history of electromechanical energy conversion, this one's like generating motor. So when they started, they still had what they still had stator when they started. They had rotor when they started, yes, and they had windings when they started. But when they started, they didn't know at that time that they were supposed to what make slots in on what the to and what embed windings into it. Okay. So what they're doing is they put the conductors on the rotor. I don't know if they use super glue to hold it or they use sellotape to hold it. I don't know, or maybe they use adhesive. I don't know what they use to hold it. But they used to put the contacts on the rotor space. Like they just there was no uh, slot on the rotor. So then, if that's the case, assuming the rotor has a diameter of say 25 centimeters, okay, and the conductor you place on the rotor, let's assume it has a diameter of what 5 centimeters. It means the rotor plus the conductor is going to give you what 6 centimeters. So that means your air gap cannot be what your air gap cannot be equal to 30 or yeah, your air gap definitely you need a bigger air gap because now if you are considering the air gap you need, you have to consider what the diameter of the rotor, consider the diameter of what the windings on the rotor. Okay, and we know from magnetic circuits that you increase your air gap, you are increasing what the reluctance of the what the magnetic field or the magnetic part. You are increasing reluctance, and if you are increasing the reluctance, it means you have to produce what more MMF, right? You have to produce more MMF in order to what a significant what flux flow in this what field. Okay, so then there were some white people who said, okay, why don't we just, if we need, just like in this, the architect you have over here, or the design we have here, we are incurring a lot of losses in what our magnetic what. So we need to reduce this. They knew that, but the question is, how do we do it? Okay, just like some of us know that this thing is bad, but we don't know what the writing should be or how the writing is done. Then some people decided that why don't we like create some small holes, push these windings into the hole. If we do that, we can be able to reduce what this gap. If we reduce the air gap for to so let's assume when it was on it for if you want to produce an MMF of what or if you want to produce a flux of let's say it's 50 Webers. Okay, you want to cause out of 15 milliwebers to flow. You will need maybe let's say it's 30 amps. Then if we are able to um, embed this into rotor and reduce this flux. Maybe to get the same 50 milliwatts, we'll just have to apply like what, maybe 20 amps. Okay, that is power we are saving, right? So then they decided to. Then they realized that okay, yeah, more efficient. So yeah, they went to the extent that now the windings on the rotor are fully embedded into what the rotor. Okay, but not everybody is happy about it. Yes, some people feel like okay, then the argument that there is a current conductor, okay, in a magnetic field, it's not actually these rotor windings that are produced at top. It is rather the rotor itself that is what producing that torque. So suppose so not agree with the fact that with this and we say that what the conductors here are not producing the torque. Whatever it is, the motor is okay. We move. Okay, so yeah, so there is a set winding for each phase of the supply. Since we have phase, each has what each of eight separate winding. Okay, let's move on. Now let's go to the twin brother of the stator, which is the rotor. Okay, so the different types of induction motors we have is based on their difference is not in the stator construction. Their difference is in what rotor construction. So for the induction motors, we have the wound rotor, the what the squirrel cage rotor. I don't know where the name squirrel came from, but yes, we came to meet it, and our children come and meet it. So let's move on. So we have types of rotors which give rise to two different action motors. In this course, we are going to focus on what the squirrel cage induction motor. But for the one rotor induction motor, have what they have what three phases on three phase armature. Okay, which are what especially sinusoidal distributed or displayed by an angle of 120 degrees, and they are all carried in one slot. So there are slots on the stator and there are slots on the rotor. Okay, yes. So the slots on the rotor carry what the armature windings, then the slots on the stator carry what the field winding. Okay. So these slots are on what the periphery of what the laminated iron cylinder. So if you look at because the man itself is cylindrical, the rotor is also what cylindrical in shape. Then there are slip rings connect what the windings what outside slip if necessary. If there is the need to connect these uh, if there is a need to connect armature circuit to an external circuit, there are springs because the armature is what the rotor and what rotor is moving. So you can just connect it directly to the rotor winding. Okay, so you need what slip rings. There are that can slip. Yes. Okay, so you have slip rings are used to connect the armature windings towards external circuits. So down to the squirrel cage. So the squirrel cage has what three phase windings, and this one the rotor is what it's so sliced and what lighted and stuck together. Okay, then the slots carry what copper bar or what aluminum. So you know the basic unit of matter is what conductor. Then these conductors come together to form coils. Then coils are put in groups for core groups. The core groups are put together to form what phases. At the end of the day, you can form the number of phases you want. Okay. So then the copper or aluminum bars that you place in the slot, they are short circuited. Okay. You have one bar which is short circuited to the other one. Okay, the bars are shorted together, so they are short circuited together at each end to form a closed cage. To a reasonable approximation, a cage A cage rotor acts like what a one rotor with what a slip connected together. Okay. So the rest, yeah, English. Okay, so the advantage is that each construction is simple, it's cheap and what. So this is how the rotor looks like. This is the rotor. Okay, this is the rotor. This is the shaft talking about. Yeah. So these are hot fins. So yeah, welded to aluminum end rings. So the aluminum bar short circuited. So these fins over here serve another purpose in that they help in cooling the rotor and the rotor windings. So you see, as they move, they are going to be blowing hot air on the windings over here to cool them. Okay, now let's talk about the rotating magnetic field that gives us what synchronous speed. Okay, so I think I've already explained this. So if one of the windings is energized with constant current, its magnetizing effect (MMF) varies sinusoidally around the core of the stator. So this is magnetic force. Okay, let's go back to the basis of what electricity. So when in SHS or JHS, those of us going to good school. Okay, we were told that there is something called electromotive force, which most of us refer to as what voltage or potential difference. Okay, so if I have 30 electrons over here and I have 5 electrons over here, the potential difference between these is okay. Density of electron here is less than density of electron here. Is okay. So therefore, the potential here is less than potential here. So if I look at potential here and I will see what a difference in potential, that's what a potential difference. Okay. So that means electrons can move from what? Point A to point B. But if these electrons, we remember a material has atoms. So if these electrons are moving, they are going to encounter what? Position, which is called what? Resistance. So in order to move an electron from point A to point B, you need certain force, you need to do certain amount of what work. So the work that in moving an electron from one to another is what we call the electromotive force. Or force field to move one electron one point to another is what we call the electromotive force. If I have electromotive force big in to move an electron this point A, point B, the movement of electrons result what we call current. Okay. So then if I want to know how much current, I need to know what the electromotive force and the resistance they are or the opposition they are going to encounter. So then this current or the flow of current is a function of what? The electromotive EMF and what the resistance was encountered. So then, if the electromotive force or the opposition is far greater than the electromotive force, then I won't be able to move the electron. Or even if I'm able to move the electron going to move is very, 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 very small. Is that okay? So we say that what resistance increase if the EMF is constant, the current is going to what reducing. The same way if I've got electromotive force with which and I have a small opposition, I'm going to move what more electrons and even move them at a what faster rate. I'm going to have high current. Is that okay? The same way, so that's what this one ohms about. Is that okay? In the same way, same thing happens in magnetic circuit. So in magnetic circuit, we don't have current flow, but we have what fast flowing. Is that okay? So these flags, too, when they're blowing in the magnetic circuit, they encounter opposition. But in magnetic circuit, we call this opposition what reluctance. Is that okay? The part is what reluctance. Okay, we call it reluctance. So then the smaller the reluctance, the more flags flow. Just as the lower the distance, the more current will flow. Okay. And in order to cause these flags to flow, I need a certain force. I need to do some amount of work. And that force is what we call the magnetic force. So this magnetic force, just like EMF, is a function of what? Um, is a function of what? Current. Okay. This magnetomotive force is a function of what? Flux. I hope that makes sense. So this MMF is equal to what? Flux, the flux times what? The reluctance. The reluctance is represented by S. This one is also equal because you need you need a current in this case to produce what? Flux. So that means the amount of current that will flow through a conductor so influences what this magnetic force and the number of turns. So when we're in JHS, we're in solenoids and things, right? My primary wasn't, so we didn't experiment. Yes. So yeah, so this magnetomotive is a function of what? The current. And this magnetomotive force, in another sense, is equal to the number of turns times the current flowing through what? The winding. Okay. So it means that for a fixed reluctance or for a fixed number of turns, as I increase current, my flux is going to what? Increase. That's if the reluctance is fixed, this is fixed. Okay. But in magnetic circuit, let me see so that in case when we get certain part, I have to explain again. You see, you can't keep increasing the current forever just because you are getting more. Life doesn't work that way. It will get to a point where the magnetic circuit is going to say, my bread. Is that okay? So when that happens, we say that the circuit is what, or the magnetic material is saturated. It means that it will get to a point when you increase this by 50%, this flash increase by what, just 10%. And our you, yes. So that's it. So this is a magnetomotive force equal to a certain constant K, depends on what the type of winding times the current times what the cause of the flat displacement around the ball. And it's also what a function of what this the pole pair. So pole is very important. Pole pair is very important. So then the number of poles determine how many times the sinusoidal pattern repeats around the ball. So you have the pole pair. Remember, we said what? If you have a north pole here, you have a south pole here, you have another north pole here, then you have another south pole here. You will see that the sinusoidal pattern of here you are going to have what, two north, two south. Okay, so the pattern of what flux you are going to produce, the pattern is going to read more than when you have like two poles. Okay, the pattern here is going to be more days. So then your magnetic force is going to be what? More. Okay. So I think, yeah, I've already explained this at the beginning that when you supply phase voltage to the stator, it's going to cause three-phase current flow. This is going to produce three-phase flux, which are displayed at an angle of 120. This flux will what interact so that because of what the angular displacement between the, okay, then we're going to produce what resultant flux, and this flux is what's going to uh, rotate at what Chronos speed. Okay, so this is the current that is the flux is given by this, and magnetic force given by this, and we can see current over here, but each current given by this. So we have phase red, phase blue, and phase yellow. The phase blue is displaced by what angle of 120 degrees. This is displaced by what? It's lagging by 120 degrees. If you are lagging by 120 degrees, it means you are leading by 120 plus 120 degrees. Is that okay? So this one, so if I'm substitute this into this, you are going to have what two functions what multiplying it that, and there is what a trick identity that you use to what solve. Okay, that one is not part of drives. So yeah, so you have a face red. So the face red mm is equal to KI I said that the amplitudes are the same. So I cos what P what phi. So you can see that the phase blue is lagging the one by what 180 degrees over here, and the phase yellow is lagging. There is phase yellow is lagging by 180 degrees. If it's by 240 degrees, if it's lagging by 140 degrees, it means it is leading by what 120 degrees. So this equal to what Ki cos E theta plus what 120 degrees. Yes, it's the same thing. Okay, it's straight. Okay. So when they interact, so now you have two cos functions on multiplying each other and use the trigger identity to separate. This is the result flux that you are going to have. It is this resultant flux is going to be what rotating at what this speed, we call what the synchronous speed. I hope this makes sense. And its amplitude is going to be 1.5 times what Ki. We saw this where this I over is just the amplitude of what the current. Okay, yes. So this is going to be the amplitude, and this is going to be what. So this is where the synchronous speed comes in. Okay. Now, at what point is this magnetomotive is going to be what? At what point, or what distance, or at what angular displacement, or at what angular distance is what magnetomotive force going to be what maximum? Now let's back to what a Jamboard. So I have MMF, MMF equals 2.5 A I cos E theta minus what omega E to T. So I want to see at what value of uh, theta, because this is as which is going to be what rotated. And this omega E here is equal to what 2 pi what FE, right? So this is a supply frequency. So if the supply frequency is fixed, it means this synchronous speed is fixed. We can't do anything about it. But we know that this magnetomotive force is going to be sinusoidal. So if it's going to be sinusoidal, at what point are we going to have what? At what point are we going to have this to be what? This magnetomotive force to be what? Maximum. There are two ways you can solve it. Because cos is a function. If cos is a function, it has values between what 0 and what 1, right? You can take like that. It has values between what 0 and 1. And in order for this to be maximum, this cos pi cos p times what theta minus omega et should be what 1. And if this should be to 1, at what value of cos or what angle will give you what that defined cos of will give you what 1? That's what cos 0. So if cos 0, then p times what theta minus omega et should be equal to 0. And if that's the case, then theta should be equal to what omega et divided by what p. Is that okay? This is one way to solve it. Another way is what if you want to show your calculus is good, you do the MMF, the theta. That's you differentiate this, then you equate it to 0. So if I differentiate this with respect to time, this is constant, right? This is constant. So I'm going to maintain it, which is what 1.5 K. And if I differentiate what cos, I'm going to get your negative sign. But here I have to differentiate what's here, the angle here. If I differentiate it, this place will go to 0. If I differentiate this part will go to become what P. And I multiply by what P. If I multiply this, so I'm going to get a negative P I times 1.5 times K, then sine what the angle here, which is of p theta minus omega what t. Then I equate this to 0. If I equate this to 0, if I divide 0 by this amplitude over here, I'm still going to get a 0. Then I'm to get a sine P P theta minus what omega E what T equal to 0. Okay, if I find the sine inverse both sides, sine inverse of 0 is 0. So I'm going to get what P theta minus what omega T equals 0. Then theta should be equal to what omega E T divided by what P. So either you go by this, which is simple, soft life. Yeah, the soft life gain we are here. Yeah. So either you use soft life or hard guy. Yeah, so let's go on. Okay, yeah, so that's it. So the peak of the MMF, as we've already proved, occurs when theta is equal to omega t divided by p. The effect is that of what? A magnetizing that is rotating at angular speed equal to what? Or an angular velocity um, of this. Is that okay? Okay, so the idea of rotating uh, flat life hard. Okay, let's go on. So we have three phases. So this is phase red. So phase red has here, this phase yellow, this is by an angle of what 20, this phase blue by an angle of what 240. Okay. So at time t equal to 0, this time t equal to 0, you can see that what red is at its what positive maximum. If it's at its positive maximum, so we are just showing the so when this you have the top, you have the bottom. So I'm sure you remember from the Chronos, we have the always one pole pitch away, right? The top and you have the down. So we're doing and how do we call it? Slots. Then you do like this. Any windings do you have here? Maybe you have down the anyway, bro. Yes, you. Yes, it's all in the past. Yes. So we can see that at time t equal to 0, the phase red it's what maximum. So it does it. Then you can see that time t equal to one on what 1/3 of the frequency. Phase zero as is at its what positive maximum. So now the maximum has switched from phase red to phase blue, phase yellow. Sorry. Then at time t equal to 2 on 3, you have phase blue having what maximum. So now maximum has so the maximum has what shifted from what or has moved from phase yellow to phase blue. So first of all, we had it over here. Now it's here. Now it is here. Then come back to red. So you can see that what the field is what rotating. Okay, it's rotating. It's not what stationary. It's what rotating. Okay. Okay. So I said that three-phase motors are self-starting and three-phase induction motors are self-starting and single-phase induction motors are self-starting. The PT. Okay. So for the three-phase, the reason why they are self-starting is because you have like three different flags. Okay, three different flags. That's what this is by an angle of 120 degrees. Okay. So then these two flags, because of the angular displacement between them, are like two different axes. So they are able to interact. And when they interact, they produce what? A result what? Magnetic field. A resultant magnetic field, which is what? Rotating. Is that okay? And you need what? A rotate flux in order to what? Cause a torque. So this rotating flux is going to induce EMF in the rotor. Then that rotor, you can also say the when EMF is induced in the rotor, current flows. Then the current is flowing through the rotor. It's also going to produce what? It's also going to produce flux. So you can have this flash interacting with the one that is already in the air gap to produce the torque, because current is proportional to flux. Or you can say that you have a current carrying factor in a magnetic field, a rotating magnetic field. then they are going to interact to produce a torque. But in the case of the single phase, you only have what one. So what happens is when you connect the single current flows, right? Which is what pulsate. It pulsates is just for single phase, but for the three phase, different pulsating what phases. So this pulsating current is going to what produce a pulsating what a pulsating flux. Okay. Then this flux is what a pulsating flux, not what a rotating flux. Because this only flux you are going to have in the air gap. So this flux is not able to what produce what a torque. Is that okay? So then doesn't mean so in your rooms, everyone's room, we all have what fans. Either it's ceiling fan, it's what the one you hold in your hand, or it's the standing fan. Whatever. Even if you buy the rubber one and you use to blow a car, it is fan. Yes. So all most of the equipment in our house, such as our blenders, like you have a lot of equipment that have what motor in them. Even your phone has what motor. Is that okay? It has motors in it. So, but these ones operate with what? Single phase. Then the question is, do you enter the phone to go and call to start? No. It's because human being is what? Wide. Some people are knowledgeable. Is that they decided that okay, we have a single phase. There is a we can split this single phase into what? Different phases. Okay. What do we have to do? We just have to make sure this flash we have, we are able to create another flash from this same flash with what? And an angular displacement. And to do that, you can use what? A capacitor. Or you can have, because motor itself is what? Inductive. Exactly. So you can introduce capacitance. If you want more uh, insight on this, go and read special machines, or you can see the special machine games and they explain it to you. So what you do, you split this one. So yeah, there are various ways. One way is what? Using the reluctance motors. Okay. Yes. Okay, so that's why single phase induction motors are not self-starting. Okay, there's a theory called the machine theory that you can use to explain this. Yes. Oh, okay, so this is a simple, I think I've already explained this operation. Apply voltage to the stator, current flow through the stator winding, then a magnetomotive force is produced which causes flux to flow through what? The magnetic circuit, the air gap. Okay, then this flux is going to what? Cut the what? The rotor. Then what cuts the rotor? EMF is induced. Okay, so what if this formula with that A is equal to BLV, maybe it's not, maybe theta or whatever. This here is what? Is velocity, is angular velocity. So it tells you that in order for EMF to be induced, there must be what? A relative motion between the interacting what components. So either the flux is moving and the conductor is stationary, or the conductor is moving and the flux is stationary. Okay. So in synchronous mode, please listen, in synchronous mode, we said that what the field, the working field is what the rotor, and armature is on what the state. Then how are we able to what? If the armature is on the stator, it is what stationary. How do we have um, how do we have EMF inducing data? So for a synchronous, this is for supply to what the root. So when you sub this into the root, that means poles of this root what the poles are fixed. So then you have what so generator you have prime mover. What the prime mover is doing, the prime mover is rotating this field. And it's rotating this field, you saw there will be what relative motion between what the flux, because flux is being rotated. So it will be rotated, then it will what cutting stationary. It will be cut the stationary armature windings. Okay. Then because they are for the three phase one, because they are arranged in phases, they are like distributed, displaced by an angle of 120. You have what EF induced in them, which is displaced by what 120 degrees. Then you have what your three phase. Is that okay? So it is that if rotor is moving at a speed equal to the speed of the um, which is the synchronous speed, it means that in this case the what no EMF induced. Okay, so I'm driving to a certain. So I'm sure we've all picked car before. If you not pick car, you pick light. So those who have picked flight, yeah, I'm not sure they've observed it, but those that pick trotro all the time, we relate. Okay, so uh, yeah, let's assume you are moving from Accra to Cape Coast. Yes, times. Yes. Then you are moving this direction. Your driver is speeding at 20 kilometers per hour. There's a certain car in front of you which is moving in that direction. They are driving at 35 kilometers per hour, right? Then you are in car A and this car B. You are in A, you are looking at car B. It's moving at what 5 kilometers per hour because relative to the speed of car B relative to you is going to be what 25 minus 20 is that which is 5 kilometers per hour. So you'll be in your car, you're like, look at how this car is moving slowly. You can't even overtake this car. It's called delusion or illusion or whatever they delusion. Hmm? Dem- Okay. Is that okay? Because you are looking at the speed of this vehicle relative to what you. Okay. So two, this car is moving at 5 kilometers per hour. And the person in this car is seeing your car be moving back at a speed of negative 5 kilometers per hour. Okay, maybe you and I we've gone too small, so we understand. But somebody's if this car is what moving back at what 5 kilometers hour, then you are going to see your to be what stationary, and you see the thing to be moving towards back 5 kilometers per hour. So that is what happens when the rotor that stands still. So that's where the slip is equal to one. The rotor is going to see the rotor is going to say rotating flux to be moved at a speed or the synchronous speed, which is what omega s. Is that okay? So then at that time, the frequency, let me say this, please pay attention. The frequency that the rotor sees is what we call the omega slip. That's the frequency, the angular frequency the rotor sees. Okay. So all the time, rotor sees what omega slip or what f slip. Is that okay? Which is we said that omega slip is equal to what? Omega s minus what? Omega r, where omega s is the synchronous speed, omega r is what? The rotor speed. So the speed that rotor sees at all time. Then at starting or at standstill, this rotor's speed is what? Zero. So then rotor seeing omega slip will see omega what? S. Is that so at starting or at standstill? The speed the rotor is standing is looking at the flux moving instead of this guy is moving fast. This guy is not what omega s is okay. So then that's going to induce what a certain EMF, and this EMF is what the rate at which uh, this flux is changing with respect to time. Then if it happens that this rotor is moving at a speed omega r equal to omega s, this rotor is going to see this flux to be ordinary. Okay, so I'll go again. The speed that the rotor is at all times was omega s minus omega r. At starting, omega r equals was zero. So then omega slip which is the frequency that the rotor is seeing, or the speed that the rotor is seeing, is what equal to omega s, which is the synchronous. So the time that the rotor has not started moving, the rotor will be standing there and we'll be seeing a flash moving. Ship, 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 ship. Like, oh, this guy is moving very fast. So he's moving at what omega s. Then that's going to induce what EMF to it. Then current to flow. Then there will be a torque produced. Then rotor will also start moving. When the rotor starts moving, now omega slip will not be equal to what? Omega s anymore. Omega slip will now be equal to what? Omega s minus what? Omega r. So then the rotor now seeing the flux to be moving at what? A reduced speed. Okay, please. You have a question, please ask. Okay, please, you raise your hand, you can ask your question. Or if it's by mistake, then let me continue. But you can unmute yourself and ask anytime. Okay, so that means as the rotors accelerate, the omega.
Please, I can't.
Okay,
I
yeah,
can't
ask.
see your screen.
You can see my screen. Then check your network, but it's not my end.
Okay, thank you.
Okay, yeah. So as the rotor accelerates, the speed, the relative speed that the rotor is seeing is what reducing. Then
Mm-hmm.
if it happens that the rotor accelerates to a speed equal to omega s, then the omega slip that the rotor will be seeing will be equal to zero. Then if that's the case, then the rotor is now going to be seeing the flux in the air gap to be what, stationary, because they are all moving at the same speed. Is that okay? That relatively, the rotor is going to see the rotor stationary. Meanwhile, is going to see the flux to be stationary. Meanwhile, the flux is not stationary. If that's the case, the ER, which is the EMF induced in the rotor, will be equal to zero, because what, there will be no change in what flux with respect to time. According to what the rotor. Is that okay? According to the rotor, the flux is not changing with respect to time. Now they are all moving at what the same speed. So then your E will be equal to zero. Okay. Now I said earlier that if your slip, so if your omega slip is equal to zero, that's omega s minus omega r is equal to zero. It means your slip is now equal to zero. S is now equal to zero. Now let's see why you are not going to produce any torque. We said that what this EMF has to be induced. Okay, this EMF has to be induced in order for EMF has to be induced in order for current to flow through the arm winding, in order for you to have torque. So then, if the rotor is now moving at the speed, at the synchronous speed, now the relative motion between them is what? Zero. It means what? Your ER will now be equal to what? Zero. If your ER is now equal to zero, it means that no EMF is in the rotor. Then if EMF is induced in the rotor, it means no current will flow towards the rotor. Okay, and we know that torque is what? Proportional to what? The current and what? The flux. So then if now there's no EMF, there's no current through the rotor, then your torque will be equal to what? Zero. Okay, so this can question, why is it that uh, induction motors are not operated at what? Zero slip? Or why is the rotor speed not allowed to be equal to the synchronous speed? It's because if that happens, your torque will be equal to what? Zero. The electromagnetic produce will be equal to zero. I hope this makes sense. Okay. Yeah, so that is okay. So now we said that I told you that what we are looking at for the squirrel cage motors. Okay, so now I have EMF induced in the rotor. Okay, EMF induced what? The rotor. So if EMF is induced in the rotor, then remember the amateur or the roto winding bars are what short circuited. So if they are short circuited and EMF induced, current is going to flow, and this current is equal to what the EMF induced divided by what the impedance. Okay, so this current IR will be equal to what ER divided by what the impedance. Where this impedance is now equal to what the resistance of the rotor winding and the what the reactive reactance of what the winding. Is that okay? And we know, so this Z over here is equal to what? R plus what? J what? XR. And XR is equal to what? XR is equal to what? 2 pi what? F LR, which LR is the what? The inductance what? The rotor. Is that okay? And this over here, 2 pi F can be written as what? Omega what? Omega. So then XR can be written as what? Omega LR. Okay. Then I said something that at starting your omega R is equal to what? Zero. And the frequency, the angular frequency that the rotor is in is that of what? Omega S or what? Omega E, which is the synchronous speed. So therefore, this will be the current that will flow at what starting. Remember, this is the current that will flow what at starting. So as we go earlier, we are going to divide this by S. I will explain how that will cover. This is the current that flows at your starting. In another term, to explain this same in because at starting, I said what at starting slip is equal to 1. Okay. So then for the other formula you have this divided by S. Slip is equal to 1, so R divided by 1 will give you what? R. But let's take it one at a time. Slow the rush. Yes. So this is the current is going to flow what at starting. Is that okay? Because at starting the frequency that the rotor is in is what omega E. Okay. Then so the jet formula for current is equal to IR is equal to what? Okay. SER or S1 whatever SER R on what S plus J omega slip for LR. So then at starting S is equal to, so this goes to 1. This goes to 1. Omega slip is equal to what? Omega E or omega S. I hope this makes sense. So at starting, this is the current that is going to be induced in the rotor. Then once this current is induced in the rotor current is now going to interact with the flux in the gap to produce what? A torque. And if this torque is enough to overcome the inertia of the motor, the rotor starts to move. Okay. Then when this rotor starts to move live. Okay. When this rotor starts to move, its aim is that I want to move at a speed equal to what synchronous speed, so that the relative speed between myself and the flux will be what? Zero. That the flux will stop what? Inducing what flux inducing what EMF in me. So I don't know about you, but me when I'm in a car, I don't want other cars to come from behind and pass. I don't like it at all. You get it? So what I like is for us to be passing by another car like film, like it's so nice. But if you are enjoying it, you know you can also die. Yes. So what this rotor does is that it tries to what accelerate to a speed equal to what the synchronous speed. Okay. So that once speed is equal to the synchronous speed, the flux will support inducing EMF in it because at that time the relative speed between the flux and the rotor will now be zero. Then the ER will be equal to what? Zero. But that will never happen. Okay. That will never happen. You can't be you can't be better than your master. You can be better than your master in some sense, but you can't have money now right now. You can't have money than your dad. That's if you don't have any other source of what and you depend solely on them. Hmm? Fine. We are recording it. Okay. Yeah. Okay. Yeah. So that's what happens. But um, the rotor never gets to what the for induction motors unless the only thing that will cause the rotor speed to be greater than or equal to the synchronous speed is if there is what a prime mover connected to what the rotor. There is an external force applied to what the rotor that can cause the rotor to what uh, go above what the synchronous speed. And in that case, you are going to have what a negative what slip. Is that okay? Okay. Now let's get into okay, so I've already explained the operation. Okay, I've already explained that at synchronous speed, if the toe moves at the synchronous speed, the torque will drop towards zero and you won't produce what any torque. So if your motor you operate the motor because you want to drive a thin load. So if you are producing zero torque, what's the essence of the motor that's running? Okay. Hey, Charlie Tuesday, Banani. Will be done very soon. Okay. So we said that as starting so the maximum EMF that will be the maximum EMF that will be induced in the rotor happens when the motor is was starting. Okay. So this explains why a very high current is what done during was starting because the maximum EMF is what produced during starting. So if the maximum EMF is produced during starting, remember your resistance and your this are fairly what constant. Okay, they may not be constant, but let's assume your impedance is constant. If your impedance is constant and you are having uh, the maximum EMF produced at starting, then you have what the maximum current flowing at starting. But as the motor accelerates, this is going to be reduced. The EMF use is going to reduce. Then the current is what going to what reduce. This makes sense. Okay. Sure. Now let's explain what we have here. So we've agreed that at in we have what the EMF is equal to change in with respect to what time. Okay. And at this point we are going to have what this value here is going to maximum because the speed of the row is equal to zero. Okay, so the relative speed or the relative change, the change is going to be what maximum. Okay. Then so that as the motor was speed increase, okay, as the speed increases, this EMF used in the rotor will start reducing. Okay. So that means at any speed, the EMF that will be used, the EMF any speed, a fraction of the what EMF produced what at start. Is that okay? I hope that's okay. So then the EMF at any speed is equal to what? Would depend on the change in the synchronous speed and the rotor speed. Okay. So we said that the EMF at any speed is equal to the slip toward the EMF that was starting. Is that okay? So at any speed equal to the slip times what? The EMF induced that was starting. Is that okay? This you see over here, this is the slip. That so E rating is equal to the slip sorry stationary. Okay, sure. So that's what you have over here. And then this nice. Okay, I've already talked about omega slip. Okay. Okay, so if that's the case, now our okay. So I told you that the frequency that the rotor sees at any time is what omega sleep, which is what omega E or omega S minus what omega R. Okay, so the current at any speed is equal to what the sleep, because that what the EMF rotating divided by what R plus what A omega sleep frequency. Rade Yakubu. Yeah, but how who's this one is working? Okay. Yes. Okay. So let's go on. So then, uh, IR at any speed will be equal to what? The EMF induced at any speed divided by what? The impedance. And because the frequency of the rotor is going to be omega sleep. So then the uh, in that reactance is going to be what? And the reactive reactance, the frequency component, the reactance is going to, we are going to use what? Omega sleep. Okay. Then times of LR. Is that okay? But if you want to write this in terms of the EMF, or like you want to write it in terms of, because there's not E rotating, but we know the E induced at was 10. So then IR at any speed, no E rotating is what? It was stationary, right? Divided by the resistance of what? Divided by the resistance of brittle plus what? J omega sleep. Omega sleep is giving us what? S omega E, because we said what? S is equal to omega E minus omega R, all divided by omega E. Now if that's the case, then S times omega E should be equal to omega E minus what? Omega R. And this is what we call what? Omega was sleep. So then I can write this way times what? LR, right? Then I can divide this by S, divide this by S, divide all this by S. So then I'm going to get IR to be equal to, if I divide S ER by S, I get what? ER, right? Divided by, then I'll divide this by what? S. Then plus, if I divide this by S, I'm going to get what? Just J omega E what? LR. Is that okay? Yeah, so this is why we've been using this to what? Solve questions. Okay. So this is the current that will flow at any speed. Okay. Okay. So, okay. So consider stationary rotor. The rotor is what? Two sets of coils sharing a common magnetic part like a transformer, right? So in this case, the stator winding is going to be what? Our primary. Then just like a transformer, where the primary and the secondary are not electrically what coupled, they are magnetically coupled. So the same way, the stator and the rotor are what? Not electrically connected, they are connected magnetically. So you have the rotor circuit over here. Is that okay? Yeah. Therefore, we can use what? A simple equivalent circuit as shown in figure 1.5. From here going, we are all the analysis we are going to do are going to be what? Per phase analysis, per phase analysis, per phase analysis. Okay, so we are assuming that what? The three phases are what? Balanced. And if the three phases are balanced, whatever we get for one phase, we can just multiply it by three, and that's going to give us what? The overall effect. Okay, so if you are looking for losses, we can calculate the losses for one phase, multiply it by three. That would be what? For the three phases. Okay, yes. Okay, so that's what we are going to do. And from transformers, when we're doing transformers, we know if you want to analyze circuit, you have to either you refer the primary to the secondary, or you refer what the secondary to the primary using what the tens ratio. Same thing applies here. So in this case, our stator is what our primary circuit. Okay, our rotor is what our secondary what circuit. Okay, so if you are going to do the analysis, it's either you refer everything to the stator side or you refer everything to what the rotor side. Okay, and in this analysis, we are going to assume what tens ratio of what 1. Okay, so yeah, you know how to do the referral. Okay, so this is what we are going to have.